In this video, I'd like to talk about the math question of the day for January 21st, 2023. And this problem here is a word problem from calculus. It requires a basic understanding of derivatives, and in fact, this is called a related rates problem. So you do need to have a general understanding of calculus to be able to solve this and an understanding of word problems. But at this point, go ahead, pause the video, give this problem your best shot, and see if you're able to come up with a solution. And when you're ready, unpause the video and we can go through this together. Now, assuming that you gave this problem a shot, we can go through the problem together. And for future videos, if you have an interesting math question of the day, I encourage you leave that in the comments and I may make a video on it if it's a good question. So with this problem, we have a thin sheet of ice that's in the form of a circle. If the ice is melting in such a way that the area of the sheet is decreasing at a rate of 0.5 square meters per second, what rate is the radius decreasing when the area of the sheet is 12 square meters? So there's a lot going on in this problem, but we can draw a simple picture. We have a thin sheet of ice that's in the form of a circle, and of course we know that since we have a circle, we know there's a radius for this circle, and we're dealing with the area of the circle, so we will need the formula for the area of a circle. This is pi multiplied by the radius of the circle squared, where pi is the circle number, approximately 3.14, and we are told that this thin sheet of ice is melting, or in other words, it is becoming smaller. And we are told the rate at which it's becoming smaller. We're told that the area is decreasing at a rate of 0.5 square meters per second. So this is where calculus comes in. We are told the rate of something, that the derivative of the area with respect to time. This is just the rate that the area is changing with respect to time. This is decreasing, so it's negative, and the rate is 0.5 square meters per second. And notice that the units match up. We have square meters for area, and we have seconds for time. And we need to know when the sheet has an area of 12 square meters, how quickly is the radius decreasing, or what is the rate that the radius is decreasing. And one of the key points with this formula here, or with this scenario, is that the area and the radius change with respect to time. So they're both functions of time. They will be different at different times. So r would be a function of time as well. And if we want, we can just rewrite this as a of t is equal to pi multiplied by r of t squared, just to put this more formally so that we know that the real independent variable here is time. Now we're looking at this scenario where the sheet has an area of 12 square meters. And in that scenario, we also need to know what the radius is. So let me make a little bit more room here. And to figure out the radius when the area is 12, we just use this formula. We can say that the area, A, is 12 square meters, and this is equal to pi multiplied by the radius squared. And from here, we just need to solve for r, but let's actually just drop the units there. We will get those back in the end. In fact, it'll just be meters since we're taking a square root of everything. But let's divide each side by pi so that we get r squared. And we'll take a square root of everything so that r is the square root of 12 over pi. And usually we would put plus or minus when taking a square root to cancel out the square. But in this case, we are dealing with the radius of a circle, which is always a positive number. So we just have the positive case. And again, this is the radius when the sheet has an area of 12 square meters. Now, to use this piece of information, that the rate at which the area is changing with respect to time is this value here, we will need to take our formula and essentially take its derivative with respect to time. And remember that we're essentially just seeing what happens when this formula, this function, changes with respect to time here. So we need to use the normal tools of differentiation, namely the chain rule. And on the left-hand side, we are just taking this area function and its derivative with respect to time. So we just get dA over dt. This is just the rate of change of the area with respect to time. And we will be able to substitute this value in. And over here, we have pi multiplied by this function. We will continue having the pi since that's just a constant that will just carry along. And taking the derivative of r of t squared with respect to t, we will need to use the chain rule. We take the derivative of the outside function, which we'll just use the power rule. We bring down the 2, and the new exponent will just be a 1, which we don't have to put. And from here, we will also need to take the derivative of the inside function, and the inner function is just r of t, and the derivative of r of t is dr dt, or we could write r prime of t. These mean the same thing, just different notations. So this equation right here is relating the rate at which the area is changing to the rate at which the radius is changing. And we're dealing with a scenario when the area of the sheet is 12 square meters. And at that time, we know what r of t is. We figured out that the radius when the area is 12 square meters is this value here, the square root of 12 over pi. So let's substitute that in, as well as our rate of change of the area. We have the rate of change of the area with respect to time would be minus 0.5, and I will drop the units here, but you can certainly keep those. This is equal to pi multiplied by 2 multiplied by the radius when the area of that sheet is 12 square meters, and we know this is just the square root of 12 over pi, and this is multiplied by the rate of change of the radius with respect to time. And this, if you recall from above, is exactly what we're trying to find. We're trying to find what the rate is of this radius when the area of that sheet is 12 square meters. So we need to solve this equation for dr dt, and at this point it's just a matter of arithmetic. We can divide each side by 2 pi, so let's rewrite this as minus 0.5 over 2 pi, and we will divide each side by this quantity here, but this will effectively result in the square root of pi over 12. We essentially just flip it, and this is equal to dr dt. And of course, if we want this as a decimal, we can compute this left-hand side to find that the rate of change of the radius with respect to time is minus 0.04071, so we'll just say 0.041, and this will be meters per second, since the radius is in terms of meters and time is in terms of seconds.